One of the most fundamental things in chemistry is stoichiometry. Stoichiometry is about when you mix things together, how much you need to mix together to get a certain amount of product. You can imagine somebody in a laboratory who's trying to make a medicine needs to know how much of his raw materials he needs to mix together to make a certain amount of medicine so he can sell it. So that's what stoichiometry is. Let's look at an example. Let's say we have a balanced chemical equation. Iron plus oxygen goes to iron oxide. This is essentially rusting. So 2 moles of iron plus 3 moles of oxygen gives you 1 mole of rust. Let's stick with moles right now. We won't worry about grams. Let's say, for example, I have 0.25 moles of iron. XS is a shorthand way of saying excess. I'm doing this in air. I have more oxygen than I can shake a stick at. Certainly more than I need. And then I want to know how many moles of rust am I going to get if I leave my 0.25 moles of iron out in the air. Okay, now the key to this are these numbers right here. Remember, that's a 1. We don't actually write it in, but it's a 1. These numbers tell me the ratios between things. Something that's in excess, I don't have to worry about. If you're thinking about, say, making a ham sandwich, if I've got a whole loaf of bread and only 2 slices of ham, the amount of sandwiches I can make is totally dependent on the ham, not on the bread. So I don't have to worry about it because there's so much of it. Well, oxygen in the air, there's a lot of it. I only have to worry about my iron. This is really a dimensional analysis problem. Now, I get my given 0.25 moles of iron. Now, moles is the key here because the only way I can compare things in a balanced chemical equation is through the moles. That's why moles were invented. And that's why these numbers are very important because they represent moles. If the given was in something other than moles, you would have to convert it to moles. If they give you moles, you don't have to do any converting, you're good. So dimensional analysis tells me moles of iron is up there, so I want moles of iron down here. And this number right here tells me it's 2 moles of iron. There's 2 moles of iron for every 3 moles of oxygen. There's also 2 moles of iron for every 1 mole of iron oxide. Which of those ratios do I want here? Well, I'm heading toward moles of iron oxide, so this is the ratio I want, 2 to 1. I don't have to worry about the oxygen at all. So 1 mole of rust. So 0.25 divided by 2 gives me my answer. 0.12 moles to 2 significant figures. There's a lot of other questions I could answer with this. I could move on from here to, well, how many moles of oxygen did that take? Now I could start either place, 0.25 moles of iron or 0.12 moles of iron oxide. It doesn't matter. They're equal to each other. That equal sign really does mean equal. But I'm going to start with this given. 0.25 moles of iron. Once again, 2 moles of iron down here. According to my stoichiometric ratio, there's a 3 there. So that's 3 moles of oxygen. And then it's 0.25 divided by 2 times 3, which is 0.38 moles of oxygen to 2 significant figures. That is the basics of stoichiometry.